Dear students, let us continue our study in this paper, which is organic spectroscopy, and in the previous module we have discussed some problems where we have applied what all we have learned in the UV visible spectroscopy, IR spectroscopy, 1H NMR spectroscopy, 13C NMR spectroscopy, and then the mass spectroscopy. And in this module also we will solve some questions and problems where we will try to elucidate the structure of the given organic compound based on the spectral data. After studying this module, you shall be able to solve problems related with the combination of these spectral information, and you shall be able to learn how to differentiate molecules specifically on the basis of IR spectroscopy in some of these cases. You shall be able to correlate the spectra with the structure of the compound and interpret the spectroscopic data. The knowledge and concepts of UV visible, IR, 1H NMR, 13C NMR and mass spectroscopy, they help us in solving problems based on the experimental data we get using these techniques. And it will help us in analyzing the experimental data to elucidate the structure of any organic compound. It can be a simple molecule or it can be a complex molecule like in our biological system. And while analyzing the data, you must keep these points in your mind. That is, when you are interpreting a UV visible spectral data, then it will give you information about the types of bonds and the electrons, because they play important role in understanding the electronic transitions which happen and give rise to the spectra. So this will give you information regarding the presence of conjugation, carbonyl group and similar other conjugated systems. If we talk about the IR values, the IR spectral values will give you information regarding the different type of functional group or groups the compound is having. The 1H NMR will be telling you about the number and the environment of the neighboring hydrogen atoms which are present. Talking about the 13C NMR, when you are given a 13C NMR spectra, it will give you information regarding the type of carbon atoms which are present in the molecule. And what can you predict from mass spectral data? It will give you information about the total mass of that particular compound and also the fragmentation pattern, and the corresponding peaks will be there, which will see how we can use all this information and derive the structure of the given compound. So let us begin with the problems now, and let us take this first question. It is, how is PMR used to establish on which carbon monochlorination of methyl ethyl ether occurs? Now if you look at the structure of methyl ethyl ether as shown here, there will be three possible products which will be there. That is, you can have the chlorination happening on methyl, and as a result you will get this CH3, CH2O, CH2Cl. Now in this case there will be a triplet and a more downfield quadret and a most downfield singlet that you will be observing. If the chlorination happens on the CH2 of ethyl group in this ether, then you get this particular product, and in this case there will be a doublet for CH3, there will be a quadret downfield for this H joined to the carbon which is further joined to Cl, and there will be a singlet for this methyl. If the product formation happens by the replacement of hydrogen of methyl of ethyl, then you get this particular product which is Cl, CH2, CH2O, CH3, and in this case there will be a singlet and two triplets, and obviously you can see the singlet will be for this particular methyl and the two triplets will be, one will be T1 for this CH2 and the other will be T2 for this particular CH2, and their downfield order will be T1 will be less than further S and then T2. Coming to the next question. The question is find the structure of an unknown compound of molecular formula C9H12. So, the molecular formula is given to you and using its 1H NMR spectra and its IR spectra which are given to you. Now, before we solve this question, let us have a look on this 1H NMR spectra. So, this is what is the 1H NMR spectra which is given to you, and the IR spectra given to you is this one. Now, how you will proceed to solve this question is, first of all, determine the degrees of unsaturation. You are already given the molecular formula which is C9H12, and when you put this C9H12 into the equation for calculating the degrees of unsaturation, you already know the formula, that is degrees of unsaturation will be equal to number of carbon multiplied by 2 plus 2, this entirely minus the number of hydrogen, and this whole divided by 2. So, when you put these values as shown here, the number of unsaturation or the degrees of unsaturation you get is 4. For non-hydrocarbon elements, we treat nitrogen atoms as half of carbon in this above equation and halides as 1 hydrogen and ignore the oxygen. So, this is in case you are having these heteroatoms, you will use this formula. Now, coming back to this molecule, that is the C9H12 as you are given in this question. Now, you have obtained that there are 4 degrees of unsaturation. With 4 or more degrees of unsaturation, obviously you can expect to find an aromatic ring in your unknown compound. So, this is a clue you can take from this information. The next step is take a look at the IR spectra as you are provided. Now, as I have told you earlier also that the IR spectra will give you information about what functional groups are there in this particular molecule. As you can see from this IR spectra, you have a jumble of peaks between 1800 and 2000 centimeter inverse, and this is indicative of an aromatic ring, and you can confirm the presence of the ring by looking at NMR at the peaks around 7 ppm. So, this is substantiating, that is both the IR and NMR spectra, they are giving you a hint that definitely there is a phenyl ring present in this molecule. The next step is now to find out how many hydrogen each set of peaks represent in the NMR spectra. To get the relative ratios, it is best to use a ruler, that is a scale. Since that is difficult here, I will tell you that the relative integration for the peaks based on the calculation using a ruler I have done for you, but the same you can do it on paper. It is 5:1:6 for these 3 sets of signals as you can see here. And since this is adding to the number of hydrogens in the molecular formula 12, we do not need to divide or multiply by some number. The peaks around 7 ppm clearly represent 5 hydrogen atoms. The peak at 3 ppm, as you can see in the spectra, they represent 1 hydrogen, and the peak around 1 ppm, they are representing 6 hydrogen atoms. So, this is what information you will derive by taking out the relative integration for the peaks from the NMR spectra. That is the next step. To find the compound fragments, first you notice the benzene peaks at around 7 ppm, and this piece of information you have already identified from the IR spectra, and we have seen this integrates for 5 hydrogen. So, from this integration value you will come to know that benzene ring is substituted exactly only at one place, that is once, since one of the ring hydrogen must be replaced by a substituent. So, now we can write this fragment which is C6H5, and there is one attachment that we have to further join to get the entire structure. Moving further, now take the molecular formula and subtract out this C6H5. The benzene substituent C6H5, once you have subtracted, what you get from C9H12 is C3H7. And note that the benzene ring contains all 4 degrees of unsaturation, 1 for the ring and 3 for the 3 double bonds. So this means there is no more rings or no more double or triple bonds that you have to place. So C3H7 is what you are left with to join. And now again have a look on the other integrations in the NMR spectra. You have a set of peaks that integrates for 1 hydrogen, and if you can write down that fragment, it will be this one. Further, the bonds coming off marked as lines are simply bonds and not attached to hydrogens here. The other peak is a doublet that integrates for 6 hydrogen. A carbon can't have 6 hydrogens coming off it. So obviously now what you can make it out is there are 2 symmetric 3 hydrogen groups, and obviously you can make 2 methyl groups out of this, and they are in chemically equivalent environment in this NMR. So what we can say is, to this now we have to further join 2 CH3s, we again get fragment, and these are symmetric. So that's how we have got all these fragments for this molecule based on the information from IR and NMR spectra provided to you. And you can again check to make sure all the atoms are accounted for by subtracting out of the total fragments from the given molecular formula, which is C9H12. That is, from C9H12 there is one benzene fragment that we have found out, which is C6H5, then there is one CH fragment that we have found out, and there are 2 CH3 fragments that we have found out, and yes, it is conforming to all the 9 carbons and 12 hydrogens required. So all the atoms are now accounted for. Now the next step is just joining them or piecing it all together. And how it will be done, let us try to understand. At this point, looking from these fragments, there is only one way. Sometimes you may have more than one possibility that you should explore all, but in this particular case, there is only one way that all these pieces can be joined together, and that is as shown here. That is, you have the phenyl ring, further you have the CH fragment, and to this carbon both the methyl groups are joined, that is, it is the isopropyl benzene. Now let us check the answer. What structure we have made? Again we will see what spectral values will be there for IR and NMR, and if they confirm, yes, it will be the correct structure. So you know this structure is correct because there was only one way to put the pieces together. But let us check the peak splitting just to make sure. For the tertiary carbon with one hydrogen, you would expect a septet, that is multiplet, that integrates for one hydrogen, and yes, the same is what is there in the spectra. And for the methyls, you will expect a doublet because of this one hydrogen in the environment. There will be a doublet which will be integrating for 6, and yes, it is the same. And for the aromatic ring, you will expect that there will be several peaks at around 7 ppm that will integrate for 5 hydrogen atoms. So we have been able to deduce the structure of this given unknown organic compound, which was C9H12 and the data given, and you have found out, yes, it is isopropyl benzene or cumene. Now let us move to another question. The question is a compound having molecular formula which is C4H10O. It gave the 1H NMR spectra or the PMR spectra consisting of 2 group of lines as multiplets with relative intensities in the ratio 3:2. The PMR spectrum of another compound having the same molecular formula exhibited 2 lines with a relative area of 9:1. Identify these substances. And obviously, looking at this, if the relative intensity is 3:2, then this is the case of diethyl ether, because the terminal 2 methyls will be coming at single peak and the 2 methylenes joined to the ethereal oxygen will be coming at the same, and their relative intensities will be 3:2, and that multiplied by a factor of 2 it gives you 6 hydrogens and 4 hydrogens respectively. Talking about this other information where you are given the relative area of 9:1. Now this will correspond to the tertiary butyl alcohol, and as you can look in the structure of tertiary butyl alcohol, the area of 1 will correspond to the hydrogen attached to oxygen, and the relative area of 9 will be corresponding to these 9 hydrogens which are in these 3 methyls in the tertiary butyl group. So that is how out of the given molecular formula C4H10O, one information you are provided is for diethyl ether where the relative ratio is 3:2 in PMR spectra, and the other information is about the compound tertiary butyl alcohol where the relative area is given to you as 9:1. Now let us move to the next question. The next question given to you is the PMR spectra of dimethyl formamide. It shows two signals, one at 2.84 and another at 3.0 delta for the methyl protons at room temperature, but a single sharp line appears at higher temperature around 165 degrees centigrade. Now you have to justify this why, and the explanation will go like this. At room temperature, the lone pair of electrons on the nitrogen atom, they increase sufficiently the double bond character of the CN bond to restrict its rotation at room temperature, and the spectrometer senses two different methyl groups, that is cis and trans, with respect to the single hydrogen on other side. But at elevated temperature, the rotation around the CN bond is so rapid that each methyl group experiences the same time average environment, and that is the reason why that at higher temperatures you will have a single sharp line, but at lower temperature you get two signals, 2.84 and 3 for the dimethyl formamide. Moving to the next question, you are provided with this spectra and you have to identify the unknown compound based on this spectral information, and you can see here the molecular ion peak is 88 mass units in this mass spectra which is provided to you, and furthermore you are also provided this IR spectra where you are given all these peaks. You can notice there is a CO stretch, there is a saturated CH stretch, there is a carbonyl band, and also you are provided with this 13C spectra where you are getting these peaks for aliphatic carbon next to some electronegative atom that you can see, and the carbonyl carbon at these specific positions. You are also provided with this 1H NMR spectra, and here you can notice one triplet, one singlet and one quadret, and the relative integration values are 2:3:3. So based on all this information you have to construct or elucidate the structure of the unknown organic compound. Let us see how we will be solving this question. First of all, let us carry out the mass spectra analysis. The integral molecular weight of the unknown compound is given to be 88. This we can clearly see from the molecular ion peak. And because this is an even number, we can interpret that the compound either has no nitrogen atoms or it has even number of nitrogen atoms. Furthermore, the highest M by Z peaks do not show any evidence of the presence of atoms like chlorine or bromine, because had chlorine or bromine been there in the compound, then there would have been two peaks of 75:25 and 50:50 ratios respectively. Looking at elemental analysis is not provided to you in this question. Let us move to how IR analysis will be done. Looking at the IR spectra, as you can see here, the absorption at 3000 centimeter inverse and not to the left, it shows only the aliphatic, that is saturated CH groups. Further, the carbonyl CO group absorbs strongly at 1740 centimeter inverse, and there are two intense peaks between 1000 and 1300 centimeter inverse, which are again indicating the carbonyl and that belonging to the ester group. Coming to the 13C NMR analysis, as you can see from the 13C NMR spectra given here, the NMR shows 4 different kinds of carbon atoms. The absorption at 172 ppm is typical of the carbonyl carbon. The upfield absorptions at 14 and 21 ppm are likely methyl and or the methylene groups, although no CH splitting patterns are given with this spectrum. The absorption at 61 ppm could be a carbon next to an electronegative atom. So, all this information we can derive from the 13C NMR spectra. Now, let us look at the 1H NMR spectra and analyze it. The NMR spectra here shows 3 different kinds of CH groups. The integration value of 2:3:3 suggests a methylene and 2 methyl groups. The CH group absorbing as a singlet cannot be next to a neighboring CH group because n plus 1 is equal to 1. So, here n is equal to 0. The upfield triplet must be next to a carbon bonded to 2 hydrogen atoms because n plus 1 you are getting 3 here. So, n you can derive as 2. And the downfield quartet must be next to carbon bonded to 3 hydrogens because here it is a quartet. The triplet integrates for 3 hydrogens, so it must be representing the CH3 group next to a methylene. The quartet integrates for 2 hydrogen atoms, so it must be a methylene group next to a methyl, and thus there is an ethyl group which is present, that is CH2 CH3. Now, let us try to have a combined analysis from all this information that we have derived from these independent spectra. The IR shows the only functional group present is an ester. There is no aromaticity or other unsaturation in this molecule except for the carbonyl, and this means that the absorption in 13C NMR at 61 ppm cannot be due to a carbon-carbon double bond group, and the carbon causing the absorption is next to the oxygen atom of the ester. The presence of a carbonyl is confirmed in the 13C NMR also. The ester group accounts for 44 AMU of the 88 integral mass. The ethyl group is on one side of the ester functional group and accounts for 29 mass unit. The remaining mass, that is 88 minus 44 minus 29, we are left with 15, and this will belong to the singlet methyl group. The methyl is obviously on the other side of the ester functional group because the quartet is so far downfield in the range of methylene 1 absorption that the methylene must be bonded to the oxygen of the ester. So, if we try to identify based on all this information, we find that this is the ethyl acetate molecule. Let us move to the next question. The question is, biphenyl exhibits a very intense absorption band epsilon maximum at 19,000 at 250 nm, but its 2,2 derivative shows absorption almost similar to orthogylene, that is lambda max 262 and epsilon max 270. Now, how will you explain this? The explanation goes like this. Since the angle of twist in biphenyl is small, therefore conjugation between the rings is not affected. Biphenyl thus shows a very intense absorption band at 250 nm, that is the K band, and the 2,2-dimethyl biphenyl with methyl substituents in ortho positions, however, is more stable in the twisted conformations as compared to biphenyl, and it suffers serious non-bonded compression from the juxtaposed substituents. Thus, the 2,2-dimethyl biphenyl may be regarded as 2 moles of orthoxylene, and hence it shows absorption similar to orthoxylene due to the loss of conjugation in the twisted conformation. Dear students, let us now summarize what we have learnt in this module. In this module, we have discussed some problems based on the information that we have got from single spectra or two spectra or multiple spectra. And what are these spectra that we have seen? They are UV, IR, 1H NMR, 13C NMR and mass. So, based on combinations of the information that we get from each of these individual spectra, we are able to derive the structure. But I will repeat this point again, that is, when you are trying to get the information from these spectra, you should always look for that from UV visible spectroscopy, you will get the information regarding the presence of conjugation, carbonyl type of groups. From IR, you will get the information what functional group is present in the particular molecule. The 1H NMR will be giving you indication about the number and the type of neighboring hydrogen atoms are present. 13C NMR will tell you about the type of different carbon atoms which are present in the molecule, and mass spectral data will give you information about the total mass and fragmentation pattern. We shall continue with some more problems in next modules. I am sure now you have become more confident in solving the problems by understanding some of these problems discussed in this and other modules.